it is possible to determine the reflection spectra of asteroids. And this is what is shown here on this diagram. Now here's the wavelength on the x-axis in micrometers and the albedo on the y-axis. And the albedo goes from something like 0.04 to 0.5. Now the individual measurements of the reflection at a certain wavelength for an asteroid are shown here as these points. For example, for Ceres here, each individual point is one measurement, or for 433 Eros, each of these points here is one reflection spectra. Now the interesting part is that reflection spectra can also be taken from meteorites in the laboratory. So for example, this reflection spectra here is the reflection spectra of Cm carbonaceous chondrites, or this reflection spectra here is the one from an L4 ordinary chondrite. And then of course it is possible to compare these two spectra. So you find that Ceres in fact looks like a Cm carbonaceous chondrite, Psyche looks like an N-type chondrite, Eros like an ordinary chondrite, Vesta like a eucrite, and Nysa like an obrite. And this is, for example, why the HED meteorites are usually referred to Vesta, because these eucrites, for example, look very similar to Vesta. And this can be done for other groups of asteroids. For example, carbonaceous chondrites are usually associated with C-type asteroids, or ordinary chondrites with S-type asteroids, and so on. So with this technique, it is possible to actually find the origin of meteorites, so the asteroids from which the meteorites originate, or at least the type of asteroid from which these meteorites originate, which is a very important information for looking at the structure at the solar system.